Hello, my name is Ben Moldenhauer, and I'm a graduate student at the University of Wisconsin-Madison under Dr. Matt Allen. Today I'm going to be presenting a variation on the restoring force surface method to estimate nonlinear stiffness and damping parameters. This is part of a project that was done in collaboration with Dan Rotkin at Sandia National Labs. So nonlinear analysis techniques are becoming a critical aspect of the design process. The ability to understand and take advantage of certain nonlinear structural behavior will allow us to produce more efficient structures that can survive in more challenging environments. A certain type of this nonlinear behavior arises from bolted joint connections, where you can see large variations in the stiffness and energy dissipation of the structure. You need nonlinear system identification techniques to accurately characterize these highly nonlinear effects, and to experimentally excite these joints to measure how they behave. Active forcing from a shaker is needed to reach the high amplitude responses where the nonlinear effects take over. The problem is, most nonlinear system ID methods either cannot process forced response or are limited to analyzing certain types of forcing, like sine dwells or slow sine sweeps. In this presentation, I'm going to be giving you a brief overview of a new nonlinear system ID method that I've been working on that produces natural frequency and damping ratio backbone curves for a structure under arbitrary forcing. First, I'll give you a summary of the math that's involved, and then show some examples of what it can do. So this nonlinear system ID method is functionally similar to another method called the restoring force surface method, or RFS, but I make a slight modification to it to fit viscous damping and stiffness parameters. So for now, I'm calling it RFSV, or restoring force surface variation. So say you have some nonlinear system in that it can be represented with a typical single degree of freedom equation of motion, but with the coefficients c and k assumed to be functions of time instead of constants. We can take a convenient form for the time-dependent c and k to be general polynomials with respect to time. You can then substitute these back into the equation of motion and move the acceleration term to the right-hand side. This can be put into a matrix form where the response and time terms are assumed to be column vectors with each row corresponding to a sample in time. With these in matrix form, the vector of polynomial coefficients can be determined by posing a least squares solution between the matrix of velocity, displacement, and time terms on the left and the forcing and acceleration term on the right. From the polynomial coefficients, you can form the time-dependent representations of c and k, and then solve for the natural frequency and damping ratio in the usual way. And now, if you can determine the amplitude at each time sample, be it from Hilbert transform or any other method, you can swap the time dependence of the modal parameters for amplitude. And now I'll go over a numerical case study to show what this process can do under ideal conditions. So what I have is a modal ion model, which is a single degree of freedom nonlinear dynamic system that has been found to closely replicate the damping and stiffness behavior of a bolted joint in microslip. So for this numerical simulation and the experimental demonstrations that I'll show next, the forcing that is applied is what's called a sine beat. The plot on the top shows the force that was applied to the I1 model and is what a typical sine beat looks like, where it's a constant frequency sine wave shaped into a pulse by a 4-term Blackman-Harris window. The advantage of using a sine beat is that it has a very narrow bandwidth in the frequency domain, so you can use them to excite specific modes of a structure to high amplitudes. And it also has a relatively quick ramp up and ramp down time, so there is typically some sort of ring down after the beat stops. And that's what you can see in the bottom plot, which is showing the velocity response to the sine beat on top. There's a section of forced response up to 20 seconds, and then a free decay after that. Now the convenient thing about the I1 model is that it has direct equations for what the natural frequency and damping ratio are during the simulated response. These are plotted here for the response that I showed on the previous slide. On the top left is natural frequency versus time, top right is damping ratio versus time, bottom left is natural frequency versus velocity amplitude, and bottom right is damping ratio versus velocity amplitude. You can see clearly in the bottom plots that the natural frequency is decreasing with higher amplitudes while the damping ratio is increasing. And now a set of dashed orange lines just showed up, and this is what I get from RFSV for this system. So as this is an idealized case, I used the force, acceleration, velocity, and displacement directly from the simulation. The actual least squares fit was done on segments of the response about 2 seconds long, with an overlap of 90%, and I fit 2 term polynomials to C and K in each time segment. These lines are what come from averaging all the overlapping portions together. You can see that they overlay almost exactly with the truth solution that we have for the I1 model. Nice. So now that we know that that RFS should work for a nonlinear system, let's see what happens with actual experimental data that I have from a cylinder plate beam structure. So the aptly named cylinder plate beam, or CPB, is a test structure at Sandia National Labs that they've used for quite a while in substructuring and nonlinear testing experiments. You can see in the image there that it consists of a beam bolted to a circular plate, which is bolted to a hollow cylinder. The interface between the plate and the cylinder is assumed to contribute most of the nonlinearity in the structural response due to all the friction between the surfaces. At the back there you can see that a shaker is attached to the end of the cylinder. This was used to excite the CPB with a variety of sine beats. These were measured by the array of accelerometers that you can see stuck all over the surface. Linear modal parameters were found by curve fitting FRFs from a low-level burst random test from the shaker. The linear mode shapes were used to modal filter the physical responses into a set of modal responses for the sine beats. And also, to get the velocity and displacement from the acceleration, it was numerically integrated in the frequency domain. So this is the first elastic mode of the cylinder plate beam. It's just a simple cantilever mode of the beam off the plate. So these plots are laid out the same as before, where the natural frequency and damping ratios versus time and velocity amplitude. For this figure, I've included results from 2 other nonlinear system ID methods called free vibe and force vibe, both initially proposed by Michael Feldman back in 1994. Both of these methods were based around the Hilbert transform and require taking 2 derivatives of the magnitude envelope and the phase of the response. Free vibe ignores external forcing, whereas force vibe takes it into account. I would say that while RFSV is functionally similar to RFS, it gives results that are more comparable to force vibe. I've also included free vibe because it is a pretty common technique that I've seen used a lot, and it's what I used before this. So this is the response of the first CPB mode to a sine beat. The linear value from the burst random test is given by the horizontal black lines in each plot. The first thing you can see is that force vibe and RFSV give very similar results, except for at the very beginning, which I'm pretty sure is due to an end effect of the fit and force vibe using the first and second derivatives of that end effect. The next thing is that with respect to amplitude, RFSV is tracing out a pretty prominent softening backbone in the natural frequency in the bottom left plot, and then an increasing and decreasing behavior in the damping ratio in the bottom right plot. Another thing is that, while we would expect the free vibe result to be pretty inaccurate during the forcing, which is primarily before about 0.5 seconds, in the ring down after that, the frequency is in good agreement with the other methods, but the damping is at a higher value. I'm fairly certain that this is due to the shaker still being attached to the structure during this ring down, so it is then being forced by the structure and is acting as a sort of energy sink that leads to an increase in the damping. Since RFSV is taking the force into account, it's able to adjust for this and lower the damping ratio to the proper modal value. And now with that corrected value, you can see how the frequency and damping are converging to the linear values at low amplitudes. And one last thing about this, you see how there's a gap in the damping curve between the ramp up and ring down portion in the bottom right plot. We think this is probably due to a small error in the scaling of the force, either from a sensor calibration issue or the mode shape coefficient used to form the modal force being slightly off. Scaling the force by even a couple of percent can shift the damping curve quite a bit. And now these are plots of running the data from a set of sine beats at a range of forcing amplitudes through RFSV. You can see that the different measurements trace out the same amplitude-dependent behavior, and that there is a clear frequency backbone again in the bottom left plot. And the damping displays the same increasing and decreasing trend in the different cases in the bottom right plot. Another thing to note here is that the data in green is from a test with such low forcing amplitude that there is no ring down, only the ramp up and ramp down of the sine beat, which is centered at 108 Hz. RFSV is able to take this and give back a legible result that agrees pretty well in frequency while being slightly off in damping at low amplitudes. So I think this is a pretty cool result for the method. And now I'll quickly show you results I have for the second CPB elastic mode, which is another cantilever mode of the beam, but now in the stiffer direction. So this is another overlay of results from responses to sine beats at various amplitudes. You can see another frequency backbone that is very clearly traced out in the bottom left plot. And while damping has a similar sort of behavior as we saw in mode 1, with the increasing and then decreasing, the gap between the values during ramp up versus ring down is much larger this time. I assume this is probably an issue with the mode shape coefficient again, and it's scaling the modal force incorrectly. But otherwise, it looks pretty good. And now the last data I'll show is for the third elastic mode, which is the first drum mode of the plate. And now here we see another frequency backbone in the amplitude plot, and again an increasing and then decreasing behavior in the damping. One note is that the purple curve has some irregularities in the ring down, probably due to some error in the measurement, like something touching the structure during the recording. Another interesting thing is that the damping appears to converge to a value below the linear value we got from the low-level burst random test. While this could be another case of the force being improperly scaled, it could also be that the low-level burst random is still high enough amplitude to slightly activate the nonlinearity and cause the damping to increase. So in conclusion, in this presentation, I gave an overview of a novel nonlinear system ID method that I'm calling RFSV. While RFSV is functionally similar to the restoring force surface method, it produces results more comparable to Feldman's force fibe method in the form of nonlinear natural frequency and damping ratio curves during free and forced response. An advantage of RFSV over force fibe is that it seems to be less prone to end effect errors. This is probably because force fibe depends on the first and second derivatives of a polynomial fit, whereas RFSV just operates directly on a polynomial fit. The numerical case study, where I simulated the response of a modal I1 model to a sine beat, showed that with ideal data, RFSV essentially perfectly models the underlying nonlinear system. In the experimental demonstration, we saw that with the first three modes of the cylinder plate beam structure, RFSV was able to produce very consistent natural frequency and damping ratio backbone curves. It is noteworthy that the difference in damping result between the ramp up and ring down portions of the response is likely due to an error in scaling the modal force, either from the mode shape coefficient or the calibration of the force sensor. And then finally, for future work, so while I've showed that RFSV was working pretty well for sine beat data, I think it could work under really any forcing, provided it is accurately measured. One case in particular I'm going to be looking at is if this could be used during phase quadrature testing to estimate the quadrature point from a safe, stable distance away. And that's all I have for you. Thank you for taking the time to listen to this recording, and I hope to hear from you in the Q&A.